this video, we're going to look at some financial applications of exponential functions. We have two objectives. First, determine the future value of a lump sum of money, and then also determine the rate of interest or time required to double a lump sum of money. We'll have three formulas to be working with. The first is just called the simple interest formula. This formula applies if interest is compounded just one time per year. And it says if a principal of P dollars is borrowed, so P is the initial amount borrowed, principal, for a period of T years, so T has to be in years, at an annual interest rate R, expressed as a decimal. Interest charged is I equals the principal times the rate times the number of years. So the way this is stated, is as interest charged on a loan, but you could also use the same formula to calculate interest paid on an investment if it's a simple interest situation. Next, we have the compound interest formula, and this would be what we would use if we have something like interest that's compounded monthly or daily or quarterly. It says the amount after T years due to a principal P invested at an annual interest rate R compounded N times per year is A, the amount, is the principal times the quantity 1 plus the rate divided by the number of compoundings raised to the number of compoundings times the number of years. So again, the time has to be in years. R is, again, a decimal. And instead of getting the interest here, what we have is the account balance, or the amount due after a certain amount of time, or the account balance after a certain amount of time for a given investment. Then we have continuous compounding, and this is saying the amount after T years due to a principal that's invested at an annual interest rate R compounded continuously is A equals P times E to the RT. So the principal times the base E raised to the power of the rate times the number of years. So again, T is in years and R is as a decimal. So what happens is as the number of compoundings increases without bounds, so as n increases and increases and increases, we approach this formula. So we say it's compounded continuously, and then we use this formula, P times the base E raised to the RT. So in example 1, we're just asked, find the amount that results from investing $400 at 6% compounded daily over a period of 3 years. So this compounded daily says that we want to use the compound interest formula. So we want to use A equals P times 1 plus R divided by N to the N times T, and we want to fill in as many values as we can. So 400, that would be the principal. 6% is the rate, but we would switch it to a decimal. Daily would mean N equals 365 days per year, and it says over a period of 3 years, so T would be 3. So we're looking at, in this case, A, the amount, and that's what we're trying to find, is 400 times 1 plus 0.06 divided by 365 to the 365 times 3. At that point, you can grab a calculator get back to the home screen here. So we want 400 times 1 plus 0.06 over 365 raised to the, we want both of these factors in parentheses, 365 times 3. We want the exponent to be that whole product. So we're getting $478.88, we'll say. And then you always want to think, does this seem reasonable? Well, sure, it's not significantly more than 400. The interest rate was 6%. We were going for 3 years. Seems reasonable. Example 2, which rate represents the better investment? 9% compounded quarterly or 9.25% compounded annually? So, what we can ask or do to answer this question is, which provides a better return on $1? If it provides a better return on $1, it will provide a better return on any investment. So 9% quarterly or 9.25%, so 9.25% compounded annually. I indicated that we could use $1 as our initial investment, and we can also use in 1 year, because if it's a better investment over 1 year, it would be a better investment over any number of years. So we'll use A equals P times 1 plus R divided by N to the NT, and in this one we'll use P equals 1, R equals 0.09, N equals 4, quarterly would be 4 times a year, and we'll use T equals 1, and we'll see what the balance is. We'll again on this side use the same pattern with different values for R and N. We'll compare the same principle, a different rate, switch that to a decimal, a different N value, just 1, and the same time. So we'll keep the investment and the time the same, but change the rate and the number of compoundings and see which one is better. So we'll have A equals 1 times 1 plus 0.09 divided by 4 to the N times T, so to the 4th. And on the other side, we'll have A equals 1 times 1 plus 0.0925 divided by 1 to the 1 times 1, so to the 1. So grab your calculator and compare these. So we'll have 1 plus 0.09 divided by 4 raised to the 4th. So that's going to give us 1.09308. And the other that we can calculate without grabbing without a calculator, it's just 1.0925. So this is a better investment. The lower value would be a better loan to take out, but this would be a better way to save your money, way to invest your money. So again, we kept the time and the principal equal for both, just changed the rates and the number of compoundings, and then we compared. We could have left this as P instead of picking a dollar value, and we could have left the T as T, and then compared that way as well. But it's fine to pick $1 and 1 year and compare. That's fine. All right, next example. How many years will it take for an initial investment of $25,000 to grow to $80,000 if the rate of interest is 8% compounded continuously? So we're looking now at compounded continuously, so we want A equals P times E to the R times T. And we want to fill in as many values as we can and then find what's left. It looks like 25,000 is our initial investment, so P would be 25,000. We want it to grow to 80,000, so we want the account balance to be 80,000. And the rate is 8%. Switch it to a decimal, and we don't know the time, so that's what we're trying to find. So we'll fill in the pieces. 80,000 equals 25,000. E to the 0.08 times t. So we have an exponential equation that we're trying to solve, and that's exactly what we did in the previous section. We know we first need to try to isolate the exponential expression. So we want to get the base and the exponent alone, which means we need to get this 25,000 out of the way. And the way to do that is to divide by it. So we'll divide both sides by 25,000. And we'll have e to the 0.08 t equals we could just do 80 divided by 25, but we'll do 80,000 divided by 25,000. We get 3.2. And then the way to finish this is to take the natural log of both sides. We can move the exponent down on the left side. And the natural log of e is just 1. So t would be the natural log of 3.2 divided by 0.08. That's not all that useful. Let's find an approximation for that value. Oops. So we've got 14.54. And that was in years always. Oops. So about 14.54 years is how long it would take to grow 25,000 to 80,000. The next example, what rate of interest compounded continuously is required to triple an investment in 15 years? So we want to use, because it says compounded continuously, P, account balance equals P times E to the R times T. And again, we fill in as many as we can. We don't know the rate, that's what we're trying to find. We know that the time is supposed to be 15 years, and we want to triple our investment. So what we want is the account balance to be 3 times the initial principal. This is how we would use the triple the investment. So we would want to solve the account balance is 3 times the initial investment. The initial investment, E to the R that we don't know, times 15. So again, the variable that we're solving for is in the exponent, so we eventually want to take the natural log of both sides. We don't want to do that until the e to the 15r's alone. So we've got 3, we'll divide both sides by p. 3 equals e to the 15r. Then take the natural log of both sides. Move that exponent down. And natural log of e is just 1. So we've got r would be the natural log of 3 divided by 15. So let's see what we get. About 7.3%, we'll say. So we need a rate of about 7.3% to triple our investment in 15 years. I'm going to look back at one of our objectives here. We said we were going to determine the rate of interest or time required to double a lump sum of money. So let's do that. So finding the time required to double a lump sum of money. If we're given an interest rate, let's say, for example, 5%. This will be very similar to what we just did. How long does it take to double our investment? And again, double our investment, that language would say then the account balance is 2 times the initial investment. And let's say we're compounded continuously. So we would set up the account balance 2p equals the principal times e to the 0.05 times t. First thing we would need to do would be divide by the principal, and we get 2 equals e to the 0.05t. Take the natural log of both sides. Move your exponent down. And natural log of e, this is just 1. So t would be natural log of 2 divided by 0.05. So about 13.86 years. So the thing that's interesting to notice about both of the last two examples is that the principal doesn't matter. The amount of time it's going to take to double the investment doesn't depend on the investment. So the investment can be any size, and it's going to take the same amount of time to double it no matter what size the initial investment is. And the same thing in the previous example, it didn't matter what the initial investment is. If we're looking at 15 years, we need the same rate to triple our investment in 15 years, no matter what that initial investment is. So you do need to memorize these three formulas, and we'll be asked to use those on your final exam.